Hello, everyone, and welcome to the 18th Surface Ventures webinar. Before I go any further, it'd be good to see where you're all joining from today. So if you could please type that in the chat box and just check that that's all working. Got a few notes in the chat already. Hello, Krish. Hello, everyone. Excellent. Good to see that is working. So just quickly introductions for myself. I am Sam McMaster, the event manager of Surface Ventures, and I'll be your host for today. Surface Ventures is a non-profit organization, and our mission is to provide world-class surface engineering education for both academia and industry. Every month, we will bring you a surface leading speaker to present the current challenges and future trends in surface engineering. Alongside that, we have workshops and live equipment demonstrations. Got lots of people saying hello in the chat. Good to see that you're all there. It's got Cyprus, Portugal, Romania. Wonderful. So today we will have three speakers from the Automotive Research Association of India, Mr. Vijay Pankwala, Dr. PK Ajit Babu, and Mr. Prasad Pail, who will be presenting an overview of the material science work performed by the Automotive Research Association of India. So in terms of agenda, we will begin with our speakers' presentations. The three of them, each one will be expected to be approximately 15 to 20 minutes, and we'll have a Q&A session at the end of the event. With regards to questions, so please type those in the chat. I have the ability to mark those for the Q&A session, and we will address those towards the end of the event. In terms of GDPR, as you will have all seen, there was a tick box to join the event. If you do not wish to receive any emails from us, you are able to unsubscribe from those. But excuse me, we'll also be releasing some application notes and brochures from Micromaterials, the partner for this event. And if you download those, someone from Micromaterials may be in touch to provide further support. As well, I would like to highlight our website, surfaceventures.org. So this features recordings of our previous talks, workshops, and information about our upcoming webinars, and a little bit of information about our team. So I would also like to just to learn a little bit more about you all. So I'd like to release this quick poll question, just asking what best describes your current position. I'll share that now. Okay, answers coming in. Wonderful. So PhD student, tenured academic, postdoctoral researcher. Wonderful. We got seems we're going to have a nice mixed audience today. Thank you very much for that. So now I would like to hand over to our first speaker, Mr. Vijay Pankwala. I'll invite you on stage now, Vijay. So.
Hello.
Oh.
Yeah, greetings everyone. This is Vijay Pankhawala from ARAI Pune. Thank you, Dr. Sam, for inviting me and our team to deliver this small talk and connect with this wonderful audience over here. So I thank you very much. Can I start my presentation?
Yes, please go ahead. I'll leave stage. If you have any issues, I will be able to come back on. Okay.
Yeah. I'm just sharing my screen. Please bear with me until then. Can you see my screen? Hello? 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 Can you see my screen?
Yes, we can see it. Okay.
Yeah. So welcome again. Our presentation is divided into three parts. I will introduce to you what ARAI is and what are our material activities, material and manufacturing activities. And my colleague, Dr. Ajit Babu, will and Prasad Phale would present one case study each. So here I go. Automotive Research Association of India was established way back in 1966 as a premium automotive R&D organization by then automotive industry and government of India coming together. To tell you, automotive industry in India that time was very nascent. We had hardly one or two manufacturers for passenger cars and as many for the two wheelers and maybe one or two just for the commercial vehicles. So that was the state of affair of automotive industry when the Automotive Research Association was established by then leaders who were really visionary, who could see that such an organization was required for the country like India, whose automotive industry is about to come up. So what started then was maybe just few researchers like Dr. Sam, 4 5 were put together by these association, and then they envision what could be the research association's institution should look like, and then they went on establishing it. It started with first establishing few facilities and then going for training. In fact, they all went for training at different places across the world, and thanks to the automotive industry worldwide over there who really invited them, taught them about the basic of automotive engineering, fundamentals of different research aspects over there. And that's how Automotive Research Association really started then. And then onwards, there is no looking back to AREI. And it started growing leaps and bounds along with the automotive industry, what it is today in India. So now, what was then just few people and one or two lab now is now a network of more than 16 to 18 research laboratories spread across three campuses in and around Pune. And we have a strong team of 750 plus team. And now our activities basically encompass almost all the aspects of automotive engineering, and it can be put into 5 different baskets as seen from the screen. The major activity we are engaging is a testing and certification, right from materials to maybe the huge vehicles. We do anything and everything, as Dr. Ajit and Prasad would put. We test from nanometers to maybe kilometers. So, and we do a country's biggest certification work. Maybe now we are doing as big as 70% of certification or homologation work for the automotive industry across the country. So that is our main activity. And we also undertake a lot of R&D and technology development projects. When I say R&D and technology development projects, these probably can be divided into three categories from a source of funding. Uh, that could be from funds coming from the industry, which we call sponsored projects, then funds coming from fully or partly from the government, that we call projects, government funded projects of national interest. And then we have internally funded projects. So these are the three category of projects. And to tell you, sponsored projects from materials area, it could be from simple failure analysis. From there to maybe it could be setting up a forging process for an industry, or it could be setting up a molding process for the industry, or it could be now the recently, I think Ajit may tell you little more about that. We are trying to help material industry to develop new alloy through ICME route. So these are the sponsored projects, category of sponsored project in materials area. I'm just giving you for an example. As regard to national interest project, that's really interesting category. In fact, ARAI has done many first time projects in the country. A very simple and very apt example could be India never had its own human body dimension database. So that time, the project was given to ARAI to create anthropometry database for the Indian human driving population. So we started from scratch. We acquired the equipment, established it. We learned ourselves. We took those equipments, the laser body scanner, all across the country, acquired the data. Now we have more than 6,000, 8,000 human body dimensions, which is now available for the industry. So this is one simple example, a typical example of national interest project. And national interest project, what we have conducted for in materials area, I will tell you in next few slides. Another area of our service category is the consulting services, where we help different organizations to undertake different kind of R&D projects, or maybe we help industry to figure out how they should go about doing their certification for a particular vehicle, or we may help a country, African country, we have helped to establish their own institution like ARAI. So anything in between, or maybe we help public sector enterprise to do business validation, or we help government to establish what we call inspection and maintenance lanes, so things like that. So this is another basket of activity that ARAI undertakes for the government and also for the people of India. Another big activity that is gaining momentum is education and training, wherein one side we have a knowledge resources library like setup, digital library, and other two areas of education and training is, one is professional training, and another is a students education. So this is a big area that we are doing. We offer a very, what we call, continued education program for the industrial professionals who want to go to higher, undertake higher education from graduation to post graduation. So we help them undertake curriculum. We have many multidisciplinary projects, multidisciplinary programs under academy. Maybe to tell you, the recent ones are being under electrical vehicles, or maybe alternate fuels, or advanced automotive technologies, things like that. The biggest, another big role that ARAI plays is we assist government of India in formulation of regulatory standards, and we also represent government and the Indian fraternity in the international forums for harmonization of regulations with the global technical regulations. So these are the typical roles. One more thing which I would like to elaborate, that recently we have started with a focused technology development activity, and we are incubating our own internal startups. We call that incubator as a technology group, and there one of the 6 focus area is around materials, wherein MPRO-D is that is material process and design is the center theme of that technology development group.
Vijay, my apologies for interrupting you.
Yeah,
Your slides have not advanced at all. Your colleagues are asking me to just to remind you of that. I don't know whether that's been a technical fault, or
you are not able to hear me.
I can hear you fine. Your slides are still stuck on on the first slide.
Oh,
So it's okay. If you can restart, you can.
I'm,
Yeah, if
I'm
you can
doing that. I'm doing
restart
that.
the presentation. There you go. Okay.
Can you see it?
There we go. Yep. So we can just start it up in presentation mode. Wonderful. There we go.
Yeah.
Excellent.
Okay.
I'll
The spectrum of activities that ARAI undertakes encompasses entire automotive engineering, right from emissions, active and passive safety, vehicle evaluation on field or in laboratory, structural dynamics, environmental research, materials and manufacturing, automotive electronics, powertrain engineering, noise vibration harshness, engineering design and simulation. And of course, I told you about academy and technology product development also. Coming to our materials activity, since its inception, we have gathered vast experience. Our team must have, I would say, distinct 1,000 plus failure analysis cases, they would have characterized more than 5,000 materials. When I'm saying it's not just simple measuring of one or two properties, but it complete characterization, as written over on the right side of them, means chemical, metallurgical, mechanical, and advanced properties like crash worthiness, fatigue creep, environmental durability, things like that. And maybe 50 plus sheet metal grades they have characterized for the crash worthiness. So this is in a nutshell, just wanting to tell you how our experience spreads out. And in material competencies, it covers ferrous, non-ferrous, plastics, uh, and of course, lately we have started with the smart materials also. In material characterization, it includes chemical, mechanical, microscopic, fatigue, environmental categories, all that. And also the other spectrum of material evaluation is for petroleum products, and even the particulate matter analysis in the air because of the exhaust emission that is taking place. So we cover petroleum products, engine coolant, brake fluid, ROHs, and particulate matter analysis. In fact, ARAI does quite a good amount of work in ambient air quality measurement and monitoring work across the country. We have done area as big as a few hundred square kilometers for air quality monitoring for a complete city or district like scenario. So that's the strength of ARAI I would like to quote over here. These are some of the facilities. These are some of the facilities that are shown, which our team uses for characterization, right from simple characterization to maybe high strength testing using digital uh, imagery or universal testing, dynamic material testing, of course, metallurgical scanning, electron microscopy, residual stress analysis. Okay, there is another wonderful thing AREI has is we have a forging research laboratory, which actually is a small forge shop. Idea is we develop forging processes by simulation. We then create it in this forging shop, actually practice it, and then we can hand over this complete process along with the tooling to the small industry. Idea is to help small industry do the forging and establish the process scientifically. That is how the setup is made. And recently, Dr. Ajit Babu has added a new facility for quenching dialectometer, where the heat treatment related studies and research work is carried out over here. On environmental research side, we have almost all that is required to undertake a characterization like FTIR spectrometer, TGAs, UV spectrometers, XRF spectrometer, GCs, things like that. I was mentioning that another project I would tell you what we have done from government funding, which could be a sort of a pre-competitive research in consortia manner. We created a material data bank for properties of automotive materials, which would then help the designers to create new applications or adapt it faster way. So we had tested more than I think 50 materials for different properties, from simple mechanical, chemical, fatigue properties, high strength rate, or high low temperature static properties, environmental properties, things like that. So this is one of the government funded project I would like to mention over here. Another project in materials area that we have recently completed, that is we converted a regular steel body bus into an aluminium lightweight structure bus, right from concept to validation and testing. And in its two version, we could achieve 37% lighter superstructure in one version and 33% lighter superstructure in the second version. Of course, it was not simple conversion and replacement. It was creating the new what you call extrusions that could be required for this, along with the aluminum extrusion industry, and creating and developing the new joints. In fact, our team is now applying for patent, or they might have already applied for the patent for the new joint technology or the solutions they have developed over there. Not only we developed the lightweight bus, we converted into an electrical bus also, and we appropriately call it elite or e-light bus. So this is the recent work in the lightweight structure that we have done. The new materials research areas I would like to mention before I hand over to Ajit and Prasad is the smart materials. Here, application of smart materials, wherein we have developed a single input, single output CISO like scenario to MIMO like scenario, that is multiple input, multiple output scenarios, wherein we are able to do active vibration control for this situation using piezoelectric actuators and sensors. So, and our team has also applied for a patent over here. So this is a new recent area that we are working. Magnesium is a new wonder material that auto industry is adapting. So in India, we are helping by undertaking to develop processes or characterize the material for other industry to use, other researchers to use, helping them to develop new alloy compositions, do material modeling, and develop applications also. That is another area. In battery materials, Ajit will tell you at detail what all we are doing, because his case study relates to that, so I'll spare it for him. In material modeling, creating material cards, libraries for finite element analysis, we are actively doing that because we found that uh, uh, material models, if they are not properly established before taking up into the simulation, that can lead to results which are unwarranted. So that activity we have started recently doing in a consortia and also in private research mode. And in forging and in heat treatment, the new things our team is working is a lightweighting route for, they have already developed a uh, lightweight connecting rod for small vehicles. Ajit can mention while doing. They are also, Ajit has also worked onto bimetal forging and he recently awarded patent for that. And we also are working on heat treatment optimization. So these are the work. And of course, we have lately started on ICME work, where now we are focusing on one side, one sponsored or two sponsored projects for new alloy development. On the other side, we are learning and also trying to establish the framework for ICME setup. Last but not the least, I would like to mention over here, ARAI being an association and a research, what we say, consortia facilitator. We have developed a technology innovation platform wherein all researchers or industries or institutes or even the government approvals can come together and they can collaborate to develop multi-domain technologies for indigenous solutions, and can also bring together the students and entire community. So this platform has been developed with the help of government, and this is already live. So this is what I wanted to mention to this. So that's it from my side. With this, now I request Dr. Ajit Babu to present his part of the case study. Over to you, Ajit. I'm stopping sharing.
Yeah.
Thank you so much for your
Thank you, sir.
attention.
I will share my screen. I hope my screen is visible.
Yes, I can see it. Please
Yeah.
go ahead.
Hello, everyone. So today I'm going to talk about a specific topic on how to develop an application-specific battery pack development for an electric vehicle, and how to do a failure analysis and why it is important. So before going, I just want to run a small animation to just tell you how a lithium-ion battery works. Now, this is a typical cross section of a lithium-ion battery. You can see it is basically lithium ions which moves from cathode to anode. Now the cell is charging, and the green dots are lithium ion. There is a solid electrolyte interface is formed on the one electrode side, the graphite side, and you can see the lithium ions are moving, and the electrons are coming from the outside, and it is being charged. So the
Dr.
typical.
Babu, my apologies for interrupting you. Would you be able to hide the event.demio is sharing your screen, please, just so that the audience can see? Thank you. My apologies.
Yeah, thank you. Yeah. And this is a discharge process, and then discharge again the lithium ions move from graphite to its metal oxide electrode, and it is connected with the current collector. So it is basically ion movement, and you get the energy basically, and this is the heart of the electric vehicle, what we can see. So if we see uh, the generation of lithium ion battery, it starts from LCO, which is used in our normal mobile phones and smart electronics, and the latest is next future is all solid state electrolyte, which is a very safe battery. We are somewhere around generation 4, that is around NMC chemistry, NMC 9.5.5, and now again LFP chemistry is going to come, which was a very safe battery. At the earlier times, it was the first battery incorporated for an electric vehicle. So this is the development, and we will focus only on lithium ion and not other chemistry like solid state or so. So in ARAI, we have a program called Electron, that is called the battery engineering program, where we try to work on all the scales of the battery technology. That is right from material level characterization, understanding it, how to do the thermal management of that material, the battery pack, and developing the algorithm for BMS development, the electronics aspect, and then we made our own pack, which is integrated into a vehicle as a technology demonstrator. So the entire application engineering area is covered, right from material characterization till vehicle integration in this program. So why we should study failure analysis of the battery? So if you see a normal metal, I understand a lot of people are working in metals. We have a lot of handbooks to refer the handbooks for in case of failure analysis. We have a data bank. But what about the electric vehicle? What about the batteries? Now, if the battery fails, we have to find out the reason for its failure, whether that is the electronics aspect, whether that is the mechanical structural aspect, or whether it is a cell, or whether it is the thermal management which it didn't perform properly. So there are so many multidisciplinary components are available within the battery pack. We need to really find the answer, and thus failure analysis becomes really important in EV, and we don't have that much data bank as compared to a metallurgical failure analysis like CVC in the ASM. So is it really a quality is an issue? This technology is evolving. We can see there are multiple accidents happening worldwide, India or some other major brands also. You can see that the cell manufacturing quality is still not no perfect. Sometimes somewhere the error comes and that costs lives. So basically we have to really understand the battery very well, whatever the vehicle is or whatever the brand is, and implement a technology application engineering such that it becomes more safer. So the battery consists of multiple material. As you can see, there are around 205 layers of battery within one single cell, that a cathode, anode, and separator. So understanding this construction becomes important. Why we want to understand this construction? If there is a battery, we have to check the performance. The performance can be functional performance or safety related performance. If it is an electrical performance of a battery pack, that can be tested physically. But what about an ongoing R&D? If we want to improve the battery pack and increase the performance well, we need a virtual platform wherein we can do our own ongoing R&D rather than going to the physical one. We need to develop the battery pack more safely for other mechanical abuse or other kind of protection during worst case scenario like crash or so. In this case, what we require is a digital twin. If we have a digital twin of the battery pack, which consists of multiple hundreds of cells, then these all work can be done properly. And in order to create the digital twin, what we need is a very good data bank, which can replicate the actual cells. So it should replicate with respect to construction of the cell. It should understand, it should tell with respect to time and with respect to different charging state, how it will behave, and how the materials will behave. So there are so many testings are available. You can see tension, bending, which can calculate the values of stress and strain on a larger scale level. So tension, 2-point bending, pin penetration, impact hammer to understand the modal analysis and so on. But the challenge is not the larger scale, it is the scale at a small scale level. So to measure the local stress and strain, so that the digital twin is the actual replica of the physical battery pack. That is the challenge, and to incorporate that in the FEA model. So is it really an important aspect to understand what is the local stress, local strain inside the lithium battery? So the reference literature says that the kinetic stresses are amounting to up to 1 MPa. The thermal stresses can go up to 100 MPa, and the manufacturing stresses induced in the cell while doing the production can go to up to 2000 MPa. And even during cycling, charging and discharging process, the structure changes. In, let's say, for in this case, LMO anode cathode can change from cubic to tetragonal phase. So when there is an expansion, there is a stresses. Even if it is a solid state electrolyte, which is considered safer than the liquid electrolyte, a penetration can happen. Lithium ion penetration, lithium metal penetration can happen, and that can cause damage to the cell. So a lot of things are happening inside the cell while using it. So stresses are generated, and we have to understand these stresses. So silicon is one of the wonder material which everyone wants to increase its quantity for better performance. But the problem with silicon is that the silicon expands a lot. 285% expansion is generally seen, and not so. These kind of materials are when it is there present in the cathode or within the battery, we have to really understand how it is performing at different point of time. Not only silicon, even the normal lithiated carbon, LFP cathode, LMO, NMC, these are different cathodes basically, and all these cathodes are expanding for certain percentage, as you can see in the number 6, 7 and 2.4%. Other than LTO is a future chemistry which is yet to be proven and come in application. So this expansion leads to stresses and strains. Thus it is important that we measure the stress and strain. So when we are studying a lithium ion cell, it becomes a multidisciplinary approach. We have so many different science involved in it. It can be simulation, modeling, electronics, thermodynamics, electrochemistry, and of course material science is one important aspect of a lithium ion battery. So today I will speak more on the material science aspect. So when I said construction, how we can do how we can understand the construction of the cell. So the basic technology which is available, characterization technology, is the tomography and radiography. So here are some of the images of the radiography where it is a 2D image. We can understand how the cell quality is, what is the construction, and so that we can maybe incorporate in the FEA model as well. And the 3D image we can get from tomography. So this is a non-destructive testing which can tell us the construction of the cell. So we create so many data bank of these images in our day-to-day work, and check after its age or after its number of cycles. So I spoke till now on the more on failure analysis important, but it is also connected to the battery pack development. So the material knowledge, whatever we are generating or are understanding, also helps us in battery pack. Let's say we are developing in battery pack for an electric vehicle. This is an Indian condition. You can see that the road is quantified based on its road roughness index, ARAI, and you can see that ARAI value, this is as per a standard, and changes for different road condition. City will be different, rough road will be different, ghat will be different. So basically this road imparts vibration to the battery pack, and what vibration, or in case of crash it could be kind of nail penetration. So this is a mechanical abuse. So what will happen if this kind of mechanical abuse happens to the battery pack, that we will see. So this is one study which we carried out. So this is a typical battery pack. This is a shaker, and we are inducing vibration. So you can see that the amplitude increases, the dynamic stiffness also increases. Just even the voltage also dropped, and the frequency, the modal analysis we carried out, and the frequency, first mode frequency also has shifted just by doing mechanical abuse. So that is the importance of understanding the effect of mechanical abuse on any battery or developing a battery pack. Similarly, not only vibration, it could be some crash, some penetration also can happen. So here we have done a morphology analysis of a typical battery at a different charge rate. You can see that the new cell anode is morphology is captured, and after that the morphology is captured at a different location, top, center, and you can see the clear differences. Since it is a nail penetration, the maximum damages happen at the center and not at the top. So this is clearly visible that the anode top and the new cell anode looks similar, but anode center has multiple cracks in it. We also did at 100% SOC, that is the full charge condition, and the cell got burst into flames. So the anode morphology has completely changed. So when we have this kind of data beforehand, when there is a failure of our battery in use case, then this data bank can be used as a reference, and we can understand what could have happened, whether it could have happened due to vibration, or whether it could have happened due to nail penetration or any other thermal or electrical abuse. So this is a typical understanding of how we can create reference images and study. So this is similar to the anode we also done for the cathode. You can see the cell cathode top and the new cell cathode is intact. So there is no damage, but the cell cathode center has multiple cracks in it. And the cell cathode, which is 100% fully charged battery, which went into flames, the cathode has fully, the morphology is completely damaged. Not only the morphology, we also did EDAX analysis at 50% SOC and 100% SOC, and we can see that the content of iron, phosphorus, oxygen, and carbon is varying before and after the abuse testing. And similarly, at 100% SOC also, the elemental distribution has changed for the cathode. And there is also, we can see that the anode has a traces of iron elements. So there is a transport has also happened from one electrode to another without any electrical connection to it. So this kind of observation creates a very good understanding on the material movement happening during abuse testing. So this is on the vibration. So the anode was found intact, but the presence of tower-like structure was observed in the electrode. You can see here, this is the central image. You can see a tower-like structure, and we could also find in the cathode, we can also see craters. So in the earlier slide, we saw that the dynamic stiffness changes, the amplitude changes. So why the dynamic stiffness changes or why the amplitude changes? That answer comes from the morphology analysis of these electrodes. So the electrode material fails a lot. We have to understand that, and it doesn't fail abruptly. It starts slowly, and the performance gets degraded. The stability decreases. The resistance layer forms. The internal resistance increases. The impedance increases, and then we can see a noticeable performance degradation in the cell. So there could be multiple reasons, as I have listed over here. It could be layer rupture, electrode separation from the current collector, and there could be cracks. Cracks could be transgranular crack or intergranular crack, and these cracks could be of due to different reasons. So we have to, when we see a crack of a battery electrode material, we should understand why this kind of crack must have happened. If it is a transgranular crack, we may say like that the abuse could be available. Abuse could be there due to which the intergranular crack has happened. Transgranular crack has happened. Sorry, but if there is an intergranular crack, that is a grain-to-grain separation has happened, means it could be due to the manufacturing quality. The adhesion between the electrode and the current collector may not be correct, and due to which the grain-to-grain separation may have been happened. Like that, we can come to an observation. So till now, whatever I spoke is on the qualitative analysis of the battery material. But apart from qualitative, we want to also go for a quantitative numbers, so that can act as a reference number once we do a failure analysis, or if we want to develop a battery packer. So in this case, we worked with the micromaterials. Thanks to them, they have helped us in developing this methodology of quantifying the battery electrode using nano indentation. So we all know nano indentation has a very good spatial resolution. It is done by Berkovich indenter and cube corner indenter. So we can calculate in nano indentation the Young's modulus, which is a property of the stiffness of the solid material. We also can understand the hardness, which is the resistance to deformation, hardness of the electrode I am talking about. And also we can understand what is the fracture toughness, that is the ability of the material to contain crack. And these electrode being chemically deposited over the current collector, it is not a homogeneous deposition. We assume that it will be heterogeneous in nature, and the construction of the cell, whether it could be a jelly roll or in a pouch cell, that also affects the homogeneity, and finally the electrode becomes heterogeneous. So understanding the values at different location of the cell electrode material also helps us a lot in developing a good understanding, also in developing a back. So people are doing so many experiments, and these are the typical values of an anode and a cathode, and also a solid state electrolyte. Researchers have carried out work in nano indentation, and these are the typical values which they have received for their battery technology, battery chemistry. So at ARI, we also did this kind of research apart from the qualitative research, wherein we carry out thermal or mechanical or electrical abuse and create a data bank out of it for different chemistries, which is further used by industries. And this is one case study wherein we used the cyclic nano indentation measurement for a failed electrode, and we could get the value with of the reduced modulus and as well as the hardness, and this helped us in correlating further with the failure and the FEA model. So this test was repeated 10 times on either sample at multiple locations to capture the heterogeneous aspect as well. So this is my last slide. So what I would like to give you a message is that it is really important to validate the performance of lithium-ion battery for its particular application. The application can be drone, or it can be automotive, or it could be stationary application. So we have to really understand the application, the load which is going to come on the battery. Then not only at one particular instant, but during the lifetime of the cell, how it is going to affect the battery, so that if there is any failure, we can carry out the failure analysis of the battery both qualitatively and quantitatively, and we will require this kind of methodology, quick quality check quantitative methodology like nano indentation and scanning electron microscopy, non-destructive testing like tomography, which can be used for cell validation. So at ARAI, we work, as I told you, we have this electron program where we work a lot on material characterization to battery management system to till the entire application specific battery pack development for different vehicles. So this is one battery pack which is a swappable battery pack for a 2 and 3 wheeler electric vehicle, which we have developed at ARAI, and we carry out this kind of projects along with multiple industry partners within India and outside India, in collaboration with multiple academic institutes. And that's it from my side. I am open to any questions. Thank you.
Okay, Prasad, you're if you like share your screen, we can proceed with your first.
Yes.
And then just to make you aware of time, it is 1:45 now. So if you could, if oops. I'll just invite it back on stage. Apologies, everyone. That's a bit technical hiccup. There we go. I can see you again. If you would like to
Yes.
share your screen, your presentation, just to make you aware, it's 1:45 now, so we have 15 minutes of time remaining. So we'll try and squeeze in some questions, but we will have to be wrapped up by.
Yeah, sure. I will try my best.
Thank you.
Hello. Greetings
So,
from ARAI. I'm Prasad Fade. I'm working in Fatigue and Materials Center of Excellence. Am I
So
audible, Sam?
Yeah, I can hear you. I cannot see your slides yet.
Yes. Okay. So is it visible now?
I think I believe it's
Just
still
a minute.
loading.
Hide.
Give it a second.
Okay. So is it visible now?
Yes, I can see that. Excellent. Thank you.
Yes. Greetings. I am Prasad Fade from ARAI, and I'm working in Fatigue and Materials Center of Excellence, and we are mostly into the material characterization, failure analysis, and advanced characterization services. So today my topic is crashworthiness analysis of lightweight materials used in automotive structures. So as all everybody is aware, lightweighting is currently the buzzword in automotive, not only in automotive but all other industries like aerospace, renewable energy, sports, etc. And the driving factors behind it are increasing fuel efficiency, reducing the greenhouse gas emissions, more and more stringent legislative requirements such as emission reduction or safety norms are coming up. And also the lightweighting will have its own performance advantages such as strength, or some of the NVH aspects will be addressed. However, the safety of occupants remain the major concern in this entire process of lightweighting. Of course, when we talk in terms of the automotive industry particularly, so this lightweighting approach will have three basically the approaches coming together and delivering the results. One is the selection of materials, optimizing the existing designs, or the generating new designs which are optimized for the functional efficiency, ease of manufacturing, etc. And also the novel innovative manufacturing processes, wherein complexity of the shape will be taken care of, formability and the joinability of the materials will come into picture, and the metallurgical treatments to increase the strength to weight ratio are particularly gaining the interest. So in this scenario, what are the new age lightweight materials that are gaining the popularity nowadays? So they are mostly into polymer and composites, like engineering plastics are there, fiber reinforced plastics are there, glass FRP, carbon FRP is there. Then non-ferrous metals are also used for non-structural applications such as aluminium. Aluminium is also used for structural applications, of course. The magnesium alloys, titanium alloys are there. Dual phase steels. In when we talk of advanced high strength steels and ultra high strength steels, definitely there will be dual phase steels, martensitic steels, ferritic or benetic steels, then trip twip, such as these kind of advanced and ultra high strength steels will be used. So in this material selection process, always the question appears in front of the designer is how to select the lightweight or the right weight. So there are basically four parameters I can enumerate here. One can be the functional aspects such as the strength of material, its stiffness, dent resistance, corrosion resistance, environmental resistance, etc. The manufacturing aspect, whether what is the machinability of that particular material, formability, joinability, weldability, etc. The ability of the material for coating or surface finish, etc. Then structural aspects, which is more important for the environment, that more important for safety of the occupant as well as for the durability. They are crashworthiness and service life or durability. And of course, the driving factor will always be there in terms of the monetary. What is the cost or availability of these materials and the manufacturing process. So when we see the automotive structure, the BIW or body in white of any car, there are basically two zones, we can say. Uh, one is these are the crumple zones, where the high energy absorption is basically the functional requirement of the materials. These are the areas which get maximum damaged in the vehicle when it is crashed. So these materials and this area is to be designed in such a way that it will absorb maximum crash energy, and the materials here should have better ductility, so that more and more deformation will be accommodated by these materials. And this is the cabin space wherein the occupants are there. So passenger compartment materials should have high strength to minimize the intrusion. So this cabin has to be very high stiffness, and it should resist maximum deformation, so that the occupant inside these cabins will remain intact in place and without much damage, or the lesser energy should be absorbed by these should be transformed to these cabins. So this brings us to the concept of crashworthiness. We are saying that these materials should be crashworthy, or the vehicle design should be crashworthy. So what is this crashworthiness actually? So it is the degree to which a vehicle will protect its occupant from effect of an accident. So in case of crash or something, the vehicle or that structure should be able to protect, safeguard its occupant it can also be called like ability of structure to protect its occupant during the impact. So its crashworthiness evaluation is usually done on two levels. One is the material evaluation and other is the structural evaluation. Of course, the structural evaluation is more time consuming. It comes in the final stage of the product development, such as crash testing of the entirely built vehicle. But the new philosophy is that it should start from the beginning of the material selection itself. So material level crashworthiness analysis is also gaining more and more popularity nowadays. So when we say crashworthiness, so here is one car that is being impacted on the static barrier in the frontal impact testing, frontal crash testing. Here we can see that the front zone is only crushing, and the occupants inside or the compartment, occupant compartment, passenger compartment is not deforming much. So in here you can see that in the structural elements or the structural members of the BIW, quite a few materials are coming in the very high strain rate regime. Now we know that the crashes are happening at very high speed, like 60 miles per hour or even more than that. And what we are testing in the laboratory are very slow strain rate testing. So definitely we have to first find out the areas where maximum strain rate is coming, and here we can see that there are these kind of members, long members, which has to absorb the maximum energy, where the strain rates are exceeding 200 per second. And the maximum area in the compartment, passenger compartment, is below 10 strain rate, we can see here, or even below 5 strain rate. So here the important aspect of the material selection becomes the strain rate sensitivity. So at different strain rates, as I explained, as we discussed just now, that the material behavior can be different at different strain rates. In laboratory, we are testing at the quasi-static velocity, which is hardly a few millimeters per minute, and the crashes are happening few miles per hour rate. So it's definitely different material behavior will be there. This difference in the material behavior with respect to these applied strain rates is called the strain rate sensitivity. How materials performance or the behavior is changing with respect to the changes in the strain rates. So in automotive crash, it has been estimated that the crash usually happens maximally at maybe 300 per second or a little more than that. And the what quasi-static testing we are doing is usually 0.001 per second. So it's pretty slower as compared to the actual crash events. So for characterizing the strain rate effects, there are different phenomena we can see. One are very slow rate testing, or I will say constant load testing, such as creep test. You must be aware, wherein the constant load is applied to the material or component and its performance is checked. To right up to very high speed tests, which are hyper velocity impact using gas guns, which are usually used in the ballistic applications in defense or nuclear applications, etc. And in automotive, crash usually comes in this zone, wherein the strain rate is 0.1 to 1000 per second, and where the dynamic tension test or the high speed testing using servo hydraulic systems is the popular tool for this. So usually materials, when they are assessed for their crashworthiness, they are usually tested in tensile mode alone. And usually we use conventional load frames in servo hydraulics testers, or split Hopkinson bar, wherein a little higher strain rate is required. And usually structural level assessment is done in compression, such as crash testing, you can say, or some kind of sub assembly level testing or component level testings are done in compression mode. So we at ARAI, Automotive Research Association of India, have this high strain rate testing facility on material level applications. So we have got Instron VHS servo hydraulic system, which works up to 20, which goes up to 20 meters per second, which is pretty fast, and it generates the strain rate of 800 per second on the material level specimen, which is very well in the automotive crash regime. For the strain measurement, we have got ultra high speed camera, which goes up to 25,000 frames per second at high resolution, and more than 600,000 frame rate per second in the reduced resolution. So usually designers are interested in engineering stress strain data, then the understanding how this material, for example, you can see the video here in the top right corner, which is showing how the material is really deforming under the applied strain rates. So you can find out or the material's behavior, the localized strains, etc. And based on this engineering stress strain data, the relevantly the simulation material model cards are generated, which can be used for further simulation, and that will be used for optimizing the designs, and it will finally reduce the time required for the vehicle level crash testing, and also the economical savings will be there. So this is something for the characterization of this high strain rate and crash worthy materials. But what are the parameters that are comes into picture for selecting this crash worthy materials? So this is very popular graph of the various steel grades. As the strength increases, usually the elongation is found to be decreasing. It reduces the ductility it means that as the strength of material is increasing, this ductility of the materials is also decreasing. And these there are here we can see that different classes of steels, such as low carbon steel, microalloyed steels, and dual phase steels. They have got different behavior in the tensile regime when they are tested in the different strain rates. So in low carbon steels, the I can say this strain rate sensitivity is very high. Nearly 2 times the strength is increasing. In microalloyed steel, it is little lesser, and in dual phase steels, it is very close. So it is very important to understand what materials you are using and where they are applied, so that you can assess them properly for their high strain rate behavior. The next stage of this material characterization at high strain rate will be material modeling. So there are different constitutive models proposed by different researchers to simulate the material behavior of in plastic deformation regions as well as in the failure region, that is after necking. So some of the popular models are Johnson Cook, Zerili Armstrong modified Johnson Cook model, and combination of JC ZA models. So these are different material parameters are derived with the mathematical processing of the data, and we usually provide these material model cards to the designers, which in turn be used for the simulation applications. So by using this material modeling, here is the difference. One case I am presenting here. This is one material which is tested for uh, slow strain rate in blue line you can see, as well as in the high strain rate, that is in the orange line you can see, with 200% per second. Now by designing this material data, by taking this material data, we can see how this simulation is really happening with the deformation of 200 per second and quasi-static data. So there is always difference in the behavior of these materials. So behavior of joining, there will be impact.
Sam,
Hello.
my apologies for interrupting. I'm just making you aware of time. So you have 1 minute, approximately 1 minute. So if you could finish, if you
Yeah,
could
sure,
draw your
certainly.
presentation to a close, please. My
Yeah,
apologies.
yeah, sure. Yeah, certainly we are coming to the end only. So we have also assessed the behavioral changes in materials
I'm sorry.
response after the welding
Yeah,
or the
I'm
joining
getting these
testing,
guys finished now. And
and
then I'll,
we can see
yeah, be
even
right
the
there.
DP dual phase steels, their strengths are reducing with the impact of this spot welding, and with the dissimilar material welding, this effect is still pronounced. So this brings us to this final conclusion. Selection of right material for the optimized performance is important, and it is always advisable to select the crash worthy materials to keep the functional requirements. Use of advanced high strength steels, AHSS, composites, and multi-material approach is essential, like what we have seen in the BIW one image, that different materials, multi-material approach is used for the different sections of the crumple zone and in the passenger compartment. Simulation techniques play important role, and material models is a very important input for these simulation techniques. And for generating these material models, experimental data should be very clearly available at the given strain rates, and joining techniques will have certainly pronounced effect in this. But while selecting all these, the challenges in front of the designer and the automotive fraternity is the cost impact. These advanced materials will have some price tag, higher price tag carrying. Also some kind of process development will be there, so time impact and cost impact will be there. Certainly there can be more environmental impact in terms of composites or plastics will be there. Developmental time will be required, which can be reduced by these kind of simulation techniques and material modeling approaches. And however, for this material modeling approach, availability of the data or the availability of experimental practical data is the key, wherein this automotive fraternity and the designing fraternity is looking forward to. So thanks. I hope I've made up in the time, and we are now open for the questions if any are there.
Thank you, Prasad. Unfortunately, due to time, unfortunately I have another appointment. My apologies all. Normally we would try to extend the event a little bit to try and answer some of these questions. However, if all of the speakers are happy for me to pass on the questions in the chat, we can do that. I just have an affirmative for that, and also for the people that ask the questions. If you are happy for me to contact you following this, I will pass on answers for that. My apologies all, but I will need yeah. Fortunately,
Okay.
time permitting. Is Dr. Babu, is that okay with you? We can
Yeah.
Can do that. Okay, so thank you everyone.
Thank
So
you.
I will pass on those questions. So with that, I would like to begin to draw this event to a close. I'd like to thank all the speakers today. Thank you very much for your both detailed and widely encompassing presentations. I greatly enjoyed today's event. Thank you very much. So thank you very much to all of you. I would also like to thank our partner for this event, Micromaterials. Just to say thank you very much to them, and also to all of our other partners without whom we would not be able to run events such as these. I would like to highlight our upcoming webinar next month on the 24th of March. I will bring up I'll bring up that now. So this is with Dr. Mario Rueda, talking on the micromechanical testing of aerospace composites. So that will be available on our website soon. And I'd also like to once again remind you all of our fortnightly newsletter, Modern Surface. So please go ahead and sign up on our website to receive that. So, and finally, with regards to that, please do take the time to tell your friends about us and your colleagues, just to try and spread the word about the work that we are doing here. So with that, I say thank you to all, and I will end the event there. Thank you very much, everyone.
Thank you.
Thanks all.
Thank you all.
Goodbye. Goodbye.
Bye.
Hope you all have a good day.